All right, so we are on page 3 of the Unit 2 packet. And on page 3 of the Unit 2 packet, we are looking at properties of light. So light really connects to the atom because, as we talked about on page 2, elements can emit different colors of light when their electrons jump from the excited state to the ground state. So when we talk about light, visible light is just one form of what is called electromagnetic radiation. Electromagnetic means that it's caused from electric and magnetic waves, essentially, or electricity and magnetism cause the waves. And so that's where this name comes from. There are different wavelengths that exist within this electromagnetic range, and they're interpreted by your eyes as different colors. So you see red, orange, yellow, etc. There are other forms of electromagnetic radiation that are not visible to the human eye, and these include all of the different ones that we see down below. So just some examples on here. Gamma rays, we talked about in Unit 1. That's a type of radioactive decay that's just pure energy that's emitted. So high energy, pretty dangerous. X-rays, if you've ever had an X-ray at a doctor's office. Ultraviolet, that's the part of sunlight that causes cancer. This is the section of light that's visible. And within visible light, this spectrum's kind of backwards of the way that we usually say the rainbow. This end is red, orange, yellow, green, blue, indigo, violet, but this is the rainbow of colors. So if this was printed in color, I only have a black and white printer, you would actually see that this is the different colors. That's why this section over here, kind of where the yellow is so light printed on here. Visible light. So after visible light, on our little spectrum down here, we have infrared. Infrared is used in night vision goggles to see heat signatures. Microwaves are used in microwave ovens to heat up food. Radio waves are used to transmit radio signals if you turn on the radio in your car. So these are just different examples of forms of light that are just not all visible to the human eye. So I'm just going to pick a couple. Other forms of electromagnetic radiation include gamma. How about ultraviolet, UV? Infrared is abbreviated as IR. So I'm just going to put a couple of those there, but all of the examples are seen down below. This whole spectrum that we see down here, all these forms of electromagnetic radiation, form what is called the electromagnetic spectrum. With the electromagnetic spectrum, a couple of things are labeled on here. Across the top, all these that have NM, which stands for nanometers, or MM, which is millimeters, or just M is meters. This is wavelength. And so what you're going to notice, a nanometer is super small, a millimeter is still pretty small, and a meter is pretty big. As we move from left to right, this is showing the wavelength increasing. So this is the side of the spectrum with a longer wavelength. That tells us the length of a wave. And over here, we have a short wavelength. So if I was just going to draw a wave with a short wavelength, it would look like this. And then a wave that had a longer wavelength would look like that. So this is kind of that spectrum. That length of the wave is changing as we move from left to right. If we also talk about energy, we know that gamma rays are super high energy. And as we move from that side towards the right side, we're actually lowering in energy. So this side over here has lower energy. That's why it's not dangerous that we have radio waves flying around all the time transmitting radio signals. It would be dangerous if we had X-rays or gamma rays just being transmitted all the time throughout our bodies. So it's just kind of a note about this spectrum. All right, going back to Ernest Rutherford, remember he came up with the model of the atom that had the nucleus with protons in the center and electrons randomly scattered throughout. His model of the atom was pretty good, but it didn't explain exactly where the electrons were. He just had them drawn scattered everywhere, and he didn't really explain what they were doing. So what the electrons did. Like, were they moving? Were they moving in patterns? Did they, stay stationary? Like, what exactly were they doing in the atom? And so Niels Bohr, he's the one who came up with the ring idea, nucleus in the center, rings of electrons around the outside. And this is based on his experiments with electrons and how they related to light. So he figured out there was a relationship between electrons and light. And remember, we talked about that on page 2. He figured out that electrons jump from nearby the nucleus to farther away when energy is put into the system, and then they relax back down again. And when they relax back down, they release energy, which we see as light. Okay. Something else that scientists were working on around this time is the dual nature of light. So light has properties of both waves and particles. So in order to better understand electrons, scientists had to better understand light as well. Okay. A couple of properties of light. First off, the speed of light is a constant. This is known as the speed limit of the universe. This is the fastest known thing to exist in the universe. We abbreviate the speed of light with the letter c to stand for the speed of light, and it's equal to 3 times 10 to the 8th meters per second. So if I wrote that in expanded notation, 3 times 10 to the 8th means I need to take the number 3, and then I need to put 8 zeros at the end of it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what that number is 300 million meters per second. Just for comparison, this might not fit on here, a meter is about a yard. So if you picture a meter stick being like a yardstick, it's about this big. Light can travel 300 million of those in a second. That's super fast. And all types of light travel at the same speed, whether it's visible light that we can see, ultraviolet, X-rays, gamma rays, anything in this electromagnetic spectrum all travels at 3 times 10 to the 8th meters per second. Okay. Another thing that we talked about a second ago was wavelength, and I used this symbol when I wrote it up above on the spectrum. Wavelength is measured in meters. It's a length, so we would measure it with meters. Scientists use the metric system, so we don't use inches and feet and yards. We use meters and centimeters instead. For wavelength, this is the distance between 2 consecutive peaks in a wave. What that really means is if I wanted to measure the wavelength, I would just start at like the top of a wave and measure how far it is to the next top. That would be a wavelength. I could also measure from the bottom of a wave to the bottom of a wave. So like here to here would also be a wavelength. We're not going to talk about period. Period is related to frequency, but we're not going to get into that. So you can just ignore where it says period. But that is how we could measure the wavelength. And it would be the same here or here if I measured it in either place. Wavelength is abbreviated with this symbol. This is called lambda. It's a Greek letter, but it just stands for wavelength. Okay. For our next one, I'm going to go ahead and change this. Sometimes you see this Greek letter nu, but a lot of times we just see F. So I'm going to change that on my packet. And I'll change it on the digital copy, so it's already changed for you. The next variable on here we see mentioned on this picture, high frequency versus low frequency. So frequency is our next term that we look at for waves. Frequency is measured as the number of peaks or the number of waves that pass a point in 1 second. This in 1 second is really important for our units. Our units for frequency are either just 1 over seconds, 1 wave per second goes by. We can also write this as s to the power of -1. So that's just a fraction property. If something's in the denominator, I can just write it to the power of -1. And then this is also named the hertz after a scientist who was working on light. We abbreviate hertz as capital H and then a lowercase z. When you tune your radio, if you're tuning into whatever station, 96.5 or something, you're actually tuning it, that's in megahertz, but that's a type of frequency. Okay. When we look at these two waves, when we look and we say which one has more waves going by per second, let's say that where it says time is showing a 1 second snapshot for both pictures, which one of the pictures has more waves going by? The top one, there's more waves packed in here, so that has a higher frequency. The bottom picture has a lower frequency, fewer waves per second. Okay. Notice that there's a relationship between frequency and wavelength. If I look at these two pictures, the top picture has a high frequency, but if I look at the length of the wave, this length is small compared to this length. So when we have a low frequency, that means we have a bigger wavelength. The waves are less frequent, so they're more spread out, so each wave is longer. Up here, when we have a higher frequency, there's more waves packed into a given amount of space, so the length of each wave is tiny. This is called an inversely proportional relationship. When one variable gets bigger, the other one gets smaller. Kind of like the more you shop, the less money you have. Is also an inversely proportional relationship. Last term on here for wave properties of light. The height of a wave is called amplitude. It's a height. It's measured in meters, just like length is. And the amplitude is always measured from the middle point. So measured from the middle. So when I say we measure the amplitude from the middle, if I draw a wave like this, I'm going to go ahead and draw that middle line in there. The amplitude is just how tall it is up, or I could have measured how far down it is, like this, as the amplitude. But I don't measure it from the very, very bottom to the very, very top. I measure it from the middle. How high up did it move, or how far down did it move? So when we're looking at these couple of variables, we just talked about this relationship between frequency and wavelength. There's actually a mathematical representation that we can use to show this relationship as well. The speed of light is equal to wavelength times frequency. We know the speed of light. It's always going to be 3 times 10 to the 8th. So that's always going to get plugged in here. And we can use this equation to then solve for either frequency or wavelength if we have the other variable. Okay. So we're going to look at a sample problem of that. So example, the yellow light given off by a sodium vapor lamp used in public lighting has a wavelength of, and here's our first variable. When I read problems, I always label what the variables are. So this number right here is wavelength, and our symbol for wavelength in our equation, wavelength, is represented as the lambda. So I'm just going to write that symbol here. That tells me that this number is going to get plugged in right where I see that lambda symbol in my equation. Okay. The next thing I want to do is continue reading the rest of the problem. So what is the frequency of this radiation? So this is what we're being asked to solve for, frequency. So if I look for frequency, I see frequency is abbreviated with an F. And this is what I don't know. That's what I'm trying to solve for. From here, we can go ahead and plug in information into our problem. And we can do this by rearranging our equation first. So I'm just going to start with our equation that I see from right up above. So I'm writing this down. And I'm going to try to figure out first what variable are we trying to solve for. So the question says, what is the frequency? I need to rearrange this equation so that frequency is going to be all by itself. Right now, frequency is stuck with the wavelength, the lambda. In order to get frequency by itself, I need to move the lambda to the other side. Right now, these are being multiplied. So in order to unmultiply, to move it away, we're going to do the opposite of multiplication, which is division of the lambda on both sides to move it to the other side. So C divided by wavelength is equal to our frequency. Once we have our equation set up, now I can just plug in the numbers from the problem and then we can solve for the answer. Okay. Before I do that, I'm just going to throw, ooh, that was my pen. That's not what I was going to throw. I'm sure these things have a name. There are these triangles that you can use to help you figure out how to rearrange an equation. And the one for this equation would look like this. So if you like these triangles and you've used these before, C is our speed of light, and then frequency and wavelength on the bottom. And if you want to figure out what your equation should look like based on which variable you're going to solve for, you would just cover up the variable you're trying to solve for and it would show you the equation. For example, if we were trying to solve for C, my equation would be wavelength times frequency because they're on the same line as each other. That's multiplication. In this problem, we were trying to solve for frequency. So if I cover that up, it would be c divided by wavelength, because the c is on top and the wavelength's on bottom. If we wanted to solve for wavelength and I covered that up, it would be c divided by f. So you can use these triangles if that helps you to rearrange your equations. All right, so f is the variable we don't know, so I'm going to write that down. And then I need c on the top and wavelength on the bottom. I labeled that I have wavelength, so I'm going to go ahead and write that down here. And then on the top I need c, and I didn't see a c given in the problem, but remember that c is a constant. C is the speed of light, and it is always 3 times 10 to the 8th. So I'm going to go ahead and write that on the top. Okay. The biggest thing to do when you're plugging this in your calculator to make sure you get the right answer is on the bottom, if you ever have an exponent, you have something that says times 10 to the power of, this has to be in parentheses in order to have it come out correctly in your calculator. So here's my calculator. I'm going to go ahead and type this in. So 3 times 10. In order to do an exponent, your calculator should have a button that looks like this, a little caret button. You can type that in, so 3 times 10 to the 8th. Sometimes your calculator, if it actually shows that your exponent is tiny in the top corner, you'd need to click this right arrow to like drop back down again, depending on your calculator. And then again, divide by this bottom part. Because it has an exponent, we have to have parentheses around that. Okay? So 5.89 times 10 to the power of, your negative sign is not the subtraction sign, so this means subtraction. Negative sign should be at the bottom. It's typically in parentheses on your calculator. So I'm going to use that, 10 to the negative 7th, and then end my parentheses, and we'll get our answer. For these ones, if you're doing Schoology problems, we'll give you some of the hints for how many to round to, but we always want to round to the same number of digits as the number given to us in the problem. So on here, 5.89 was 3 digits, so 5.89, and I'm not counting the exponent part, just this. Because the number given to us in the problem had 3 digits, my answer should also have 3 digits. So when I look at this, I'm going to write down 5.09. After the 9 is a 3, that rounds down, so 5.09. And then don't forget to read over to the very end of the problem, because this says e to the 14th. E means times 10 to the power of, and then 14. So that doesn't count as part of my 3 digits, but I do have to write that down because that makes a huge difference. Is the answer 5 or 5 with 14 zeros at the end of it? Okay. So this is our answer for frequency, and our last thing to do would just be to put units on it. So you can pick any of these units, 1 over s, s to the power of -1, or hz for hertz. I'm going to pick hertz. All right, so that's one problem. There's a couple more problems on page 5. So I'll have a separate video if you wanted to look at any more examples of how to solve for these types of problems.